Hey there, welcome back to the channel. So we have covered these sub-chapters, and today we'll be covering these three sub-chapters. And this is just the learning phase, and we'll be starting the project soon. We have to cover this chapter, the references and pointers, and there is another chapter which is about more semantics, unique pointers, shared pointers, and whatnot. So I have to also cover that, and then we can start the project. Maybe I'll cover classes. Maybe I'm not sure. I just have to look at the what the content is. But yeah, I guess that is it. Let's go ahead. Okay, a function that is caller communicates with each other via two mechanisms, parameters and return values. When a function is called, when a function is called, the caller provides arguments which the function receives via parameters. These arguments can be passed by value, reference, or address, as we looked. Typically, we'll pass arguments by value or const reference, but there are times when we may need to do otherwise. In parameters, in most cases, a function parameter is used only to receive an input from the caller. Parameters that are used only for receiving input from the caller are sometimes called in parameters. So this is the case. This is passed by value. X is an in parameter, and const string s. Since it's const, s is an in parameter. Cool. Are typically passed by value or const reference. Out parameters. A function argument passed by non-const reference or by pointer to non-const. Wait. A function argument passed by non-const reference or by pointer to non-const. Okay. Allows a function to modify the value of an object passed as an argument. This provides a way for a function to return data back to the caller in cases where using a return value is not sufficient for some reason. A function parameter that is used only for the purpose of returning information back to the caller is called the out parameter. Okay, so sine 0, cos 0, degrees, enter the number of degrees, get sine cos, degrees sine cos. Okay, okay, so this is pi, radians is this. Yeah, it's radians is like degrees times pi divided by 180. Yeah, cool. And sine is stood sine, boom, boom, boom. Cool. And then since they are passed by reference over here, so sine out and cos out, the values will be modified over here also. So as you can see, sine and cos values are 0, but when we'll print the sine and cos again, the values are changed. Where is the output? Oh, there's no output. Okay, cool. Oh yeah, right. There should be an output because this is okay. Let me run this program. Okay, so let's say, yeah, enter the number of degrees. So it's 30. Sine is zero point 0.5, which is correct, right? Sine 30 is 1 by 2. Yeah. And so now if I run this again and I write 60, I should see the cost is zero point 0.5. Yeah, correct. If I do 45, I should see both of the values same. Correct. If I do sine 30, 40, 60, yeah, let's do 0. So I should see 0 and 1. Yeah. And if I do 90, I should see 1 and 0. What? Cos 90 is supposed to be 0, boys. This might be because of the floating point math. Yeah, most probably it's because of that. Okay, so yeah, just give me a minute. Okay, so welcome back. Uh, we have, okay, so yeah, over here. This function has one parameter degrees whose argument is passed by value as input and returns two parameters by reference as output. We have named these out parameters with the suffix out to denote that they are out parameters. This helps remind the caller that the initial values passed to these parameters doesn't matter and that we should expect them to be overwritten. By convention, output parameters are typically the rightmost parameters. Okay. Hmm. Let's explore how this works in more detail. First, the main function creates local variables time will cost. Uh, uh, I'll speed run this. Yeah, has access to the sign, not to copy this according to the someone. Yeah, cool. I actually know this stuff. Okay, yeah, cool. As an aside, this answer on Stack Overflow is an interesting read that explains why non-const invalid references are not allowed to bind to R-value temporary objects due to implicit type conversion, producing unexpected behavior when combined with in-out reference. Okay, let's look at that. Yeah, okay, why is it illegal to take the address of an R-value temporary? According to how to get around the warning, R-value used as an L-value, Visual Studio will merely warn on code such as this. Okay, okay, so foo and bar. So bar returns 3 and we pass in. Oh, okay. In C++, it is not allowed to take the address of a temporary, yeah, or at least of an object referring to an R-value expression, and I thought that this was because temporaries are not guaranteed to even have a storage. But then, although diagnostics may be represented in a form the compiler chooses, I would still have expected MSVS to error rather than warn in such cases. So are temporaries guaranteed to have storage, and if so, why is the above code disallowed in the first place? Actually, in the original language design, it was allowed to take the address of a temporary. As you have noticed correctly, there is no technical reason for not allowing this. And MSVC still allows it today through a non-static business extension. The reason why C++ made it illegal to is that binding reference to temporaries clashes with another C++ language feature that was inherited from C, implicit type conversion. Consider this. Okay, so in stuff, calculate stuff, we pass in O. Okay, int was converted to long over here. This won't compile in ISO C++. Long result output equal to result. Okay, cool. Calculate stuff is supposed to return its result via output parameter. But what really happens is this. The function accepts a long and, which is uh, a reference. So it accepts a long reference. So a copy of stuff will be created. So how will it? Yeah, okay. What is given an argument of type int. Through C's implicit type conversion, that int is now implicitly converted to a variable of type long, creating an unnamed temporary in the process. So instead of the variable stuff, the function really operates on an unnamed temporary, and all side effects applied by the function will be lost once that temporary is destroyed. The value of the variable stuff never changes. Yes, correct. References were introduced in C to allow operator overloading because from the caller's point of view, they are syntactically identical to by-value calls. Wait, references were introduced to C++ to allow operator overloading because from the caller's point of view, they are syntactically identical to by-value calls as opposed to pointer calls, which require an explicit and on the caller side. Unfortunately, it is exactly that syntactical equivalence that leads to troubles when combined with C's implicit type conversion. Since Stroudstrup wanted to keep both features, references and C compatibility, he introduced the rule we all know today. Unnamed temporaries only bind to const references, which is correct. With that additional rule, the above sample no longer compiles, since the problem only occurs when the function applies side effects to a reference parameter. It is safe to bind un it is still safe to bind unnamed temporaries to const references, which is therefore still allowed. Yes, it is allowed. This whole story is also described in chapter 3.7 of Design and Evolution of C++. The reason to allow references to be initialized by non-L values. The reason to allow references to be initialized by non-L values was to allow the distinction between call by value and call by reference to be detailed specified whether for const references this is possible, for non-const references it is not. For release 2.0, the definition of C++ was changed to reflect this. Was this called CPU, but I can't remember right now. Maybe someone can help you out. Hmm. Try to tell the values of the stack that so it doesn't really matter. Okay, I have some idea, but okay. Out parameters have an unnatural usage syntax. Out parameters, while functional, have a few downsides. First, the caller must instantiate and initialize objects and pass them as arguments. Yes, even if it doesn't intend to use them, these objects must be able to be assigned to, which means they can't be made const. Second, because the caller must pass in objects, these values can't be used as temporaries or easily uh, used in a single expression. The following example shows both of these downsides. Okay, maybe unused. So int x get by value, yeah, get by value, we get x equal to 5, but we did not pass anything. Oh, sorry, this is the get by value. I'm so sorry. So it returns a 5, we get 5, x is initialized to 5, get by value, can use temporary return value in expression. Yep. So int y, get by reference, y, boom, boom. Okay, then pass to function to assign the desired value. Y can be used, can only use them, and only then can we use that value. Okay, as you can see, the syntax for out parameter is a bit unnatural. Out parameters by reference don't make it obvious the arguments will be modified. When we assign a function's return value to an object, it is clear that the value of the object is being modified. When we assign a function's return value to an object, it is clear that the value of the object is unmodified. Obvious x is being modified. This is good as it makes it clear that we should expect the value of x to change. However, let's take a look at the function called to get sen cos in the example above. Yeah, we are not sure whether degrees is getting modified or sign variable or cos variable. It is not clear from the function call that degree is a parameter, but sign and cos are out parameters. Yeah. If the caller does not realize that sign and cos will be modified, a semantic error will likely result. Using pass by address instead of pass by reference can, in some case, help out parameter more obvious by requiring the caller to pass in the address of the object as arguments. Oh yeah, that is cool because when you are calling like a function, you know that it will be modified, or maybe it has some. So here it's obvious. Sorry. So here, as you can see, we are passing I through foo1. Foo1, we are there is no reference or pointer, so this is just a copy of I is created. So we know that it won't be modified. In this case, we are passing by reference, so we are not sure uh, whether it will be modified or not. For 3, we know for sure it will be modified. So in pointer, address of I, we get a pointer, boom, can modify I, not obvious. Directly sending a pointer, directly sending an address. This is also can modify, not obvious, just like reference. Note that in the call to foo3 and I, uh, this one. We have to pass in uh, ampersand I rather than I, which helps make it clear that we should expect I to be modified. Or that is not foolproof, as foo3 pointer allows foo3 to modify I and does not require the caller to take the address of PTO. The caller may also think they can pass a null pointer or a null pointer as an invalid argument when this is disallowed, as a valid argument when this is disallowed, and the function is now required to do null pointer checking and handling, which adds more complexity. This needs to be added. This needs to add. This needs to be added. Null pointer handling often causes more issues than just sticking with pass by reference. For all of these reasons, out parameters should be avoided unless no other good options exist. Best practice: avoid out parameters except in the rare cases where no better options exist. Prefer pass by reference for non-optional out parameters. In-out parameters: in cases where a function will actually use the value of an out parameter before overwriting its value, such a parameter is called an in-out parameter. In-out parameters work identically to out parameters and have all the same challenges. When to pass by non-const reference. If you're going to pass by reference in order to avoid making a copy of the argument, you should almost always pass back to the const reference. Yeah, so that it won't be modified. In the following note, we will use foo to represent some type that we care about. For now, you can imagine foo as a type alias for a type of your choice, example string. Yeah, okay. However, there are two primary causes. However, there are two primary cases where pass by non-const reference may be a better choice. Hmm. First, use pass by non-const reference when a parameter is an in-out parameter. Yeah, sure. Since we are already passing in the object, we need backout. It's often more straightforward and performant to just modify that object. Yeah, in-out, modify in-out, boom, boom, cool. Foo modified after this call may not be obvious. Uh, Give the function good name can help. Modify foo. Yep, cool. Foo modified after this call is slightly more obvious. The alternative is to pass the object value or const reference instead as per usual, and return a new object by value, which then caller can then assign back to the original object. Yeah, this has the benefit of using the more conventional return syntax, but requires making two extra copies, so that the compiler can optimize one of those copies away. Second, use pass by non-const reference when the function would otherwise return an object by value to a caller, but making a copy of that object is extremely expensive, especially if the function is called many times in a performance critical section of the code. So yeah, it use pass by non-const reference when a function would otherwise return an object value to the caller. Oh yeah, cool. So here they were returning stuff. Sorry, there we go. Yeah. So here we were giving const reference and then we are returning the stuff, but still two extra copies are created. When we create this, and then we create a copy of foo over here, and then for returning and assign, and this is assigned. So extra two copies are created, and here nothing is created. Just in the initial part. For advanced readers, sorry, there's a mosquito. Just give me a minute. Hello, hello, welcome back to the channel. Okay, yeah, okay. Let's get back right into it. Just give me a minute. Okay, okay. Recording. Audible, audible, audible. Recording, recording, recording. Cool. 20 minutes in. Okay. Yeah, for advanced readers, the most common example of the above is where a function needs to fill a large C-star array or std array with data, and the array has an expensive to copy element types. We discuss arrays in a future chapter. That said, objects are rarely so expensive to copy that resorting to non-conventional methods of returning those objects is worthwhile. Yeah. Type reduction with pointer references and const. Let's go. Okay. Let's take a look like how big is this chapter is. Yeah, okay, standard. Okay, let's go. Most of it is code. That's what I like. Yeah. Okay. Type directions for objects using the auto keyword. Oh, this is about auto. Okay. We discuss how the auto keyword can be used to have the compiler deduce the type of the variable from the initializer. Cool. So auto be deduced as an int. Cool. We also noted that by default type directions will drop const from types. So yeah, this is just double. B as a type double const drop, and this is just double. B as a type const drop. Const or const expr can be reapplied by adding the const or const expr qualifier to the definition of the deduced type. So okay, const auto. B as a type const. Cool. Uh, const expr double const auto. This is just const, and const expr auto. This is const expr as well. D is const double, const drop, const reapply, const expr, const drop, const expr reapply. Cool. Tab reduction stops references. Yeah, auto ref. Yeah, definitely. It will just like create a copy. Tab reduce a straight string, not a straight string. And ampersand. Okay. In the above code, variable references are used for type reduction. Although the function getRef returns a straight string ampersand, the reference qualifier is dropped, so the type of reference is deduced as a straight string. Just like with drop const, if you want if you want the deduced type to be reference, you can reapply the reference at the point of definition. So auto and yeah, this get reference auto reference dropped, reference reapply. Cool. Top level const and low level const. Okay. A top level const is a const qualifier that applies to an object itself. For example, top level const is a const qualifier that applies to an object itself. Okay. Yeah, that's yeah. We heard about this. I did not understand at first, but okay, I understand. So const int x, what it does is that the x is const now, it cannot be modified, and we write int pointer const pointer. So ptr, right, const applies to x, so it is the top level. Const applies to pointer, yeah. So we cannot so ptr variable cannot be modified. So ptr is equal to and of x. So ptr cannot be equal to and of y will fail completely. Yeah. If I had to show this, let's go. Yeah, okay. So let's say int a10, int b, int pointer b is equal to oh, so address of a, and let's say this was const. So if this is const, I cannot modify the value of a. Okay, so let's try. So uh, uh, how about we not do that? So if we just do dereferencing b plus plus, Yeah, dereferencing B plus plus. As you can see, read-only variable is not assignable. But what we can do is, if I created int c, which is 11, I can change the value over there. So if I do this, which is b is equal to and c, this is allowed. Look, this is allowed. But if I do this, oh, I'm so sorry, I will get error. Cannot assign a variable b with a const qualified type int pointer const. See? But now this is allowed. It should be 11. Yeah. So if you do not understand, if I do this 99, I should see a value of 100. Yeah. Const int x applies to x, and int pointer const pointer int int pointer const pointer applies to ptr. References don't have top level const syntax as they are implicitly top level const. Yeah. Uh, yeah. In contrast, a low level const is a const qualifier that applies to the object being referenced or pointed to. Hmm. So this is the top level. This const applies to x, so it is top level. This const applies to pointer, so it is top level. References, yeah, yeah, okay, cool, cool, cool. In contrast, a low-level const is a const qualifier that applies to the object being referenced to or pointed to. Yeah, okay. So because of this, the pointer cannot be modified. Constant pointer. Yeah, because of this, like we get an error because now this, because after doing this, this is a low level, so A cannot be modified. So uh, B can be modified, but A cannot be. And when we are doing dereferencing plus plus, we are trying to modify A, hence it is not allowed. Cool. And such in the case of this. This const applies to the object being referenced, so it is low level. Yep, so it is low level. Cool. Whatever it is the reference of, it cannot be modified. A reference to a const value is always a low level constant. A reference to okay, a pointer can have a top level, low level, or both kinds of const. Yeah, look at this. Look at this dude. The left const is a low level and the right const is a top level. When we say time directions drops const qualifiers, it only drops top level constants. Okay, low level consts are not dropped. We'll see examples of this. Okay, so you're saying low level consts are not dropped. Okay, let's test that. How about that? How will we test that? Hmm. Okay, I'll write a function that returns an int pointer, which returns a const int pointer const. So I have a temp. So let's say I have mm, yeah, just it's a simple function. Return let's say int pointer. I don't have to create a function for that, you know. If I do this const int pointer const x, which is the address of A, and I do auto uh, y is equal to x. So they are saying the top level one is removed, but I still can't modify them. So if I try to print x, that is possible. Yeah, cool, but I can't modify it. So low level const is still applied, so I cannot do this. Oh, I should have done this. Yeah, I still get the output. It's an int pointer though. Oh, I'm so sorry. Yeah, it's an address, and if I dereference it now, I should see the value. I mistakenly passed in the address of the pointer. Yeah. So I can modify it. So y is equal to, let's say, int c is 11, and I write const again, const int pointer const z is the address of c. I can change this. So y is equal to c, and I will get the output to 11. Convertible integer to pointer conversion from int to the address with and. Okay. Oh yeah, yeah. Sorry, my bad. I should see 11. Yeah, cool. But I cannot modify it. So if I write this, no level const still applies. Boom. Error. Read only variable. Cool. Uh, Type redirections are cost references. If the initializer is a reference to const, the reference is dropped first. If the initializer is a reference to const, the reference is dropped first and then reapplied if applicable, and then any top level const is dropped from the result. Okay, so if it's const and it's a string string, so a reference is dropped first, so it's converted to string string, and then we also remove the const, so it's just normal string string. Reference drop, then a top level const dropped from result. Cool. In the above example, since get const reference returns a const string and the reference is dropped first, leaving us with a const string. This const is now top level const, so it is also dropped, leaving the type reduce as type const string. Key inside dropping a reference may change a low level const to a top level const. Dropping a reference may change a low level const to a top level const. Const string is a low level const, but dropping the reference yields. Yeah. Oh, right. References don't have top level const. So const this is a low level const saying that like you cannot modify the value in there. So it's a low level const, but dropping the reference yields this const string, which is a top level const. And boom, it's removed. Cool. Some function that returns a const reference. Auto reference one get const reference, string. Cool. Const auto get reference, const reapplied, and it's const string. Reference 3, auto reference, so const string reference. Reference dropped and reapplied. Learn will const dropped, not const not dropped. Reference dropped and reapplied. Learn will const not dropped. Reference dropped, and in this case, both of them. So reference dropped and reapplied, low level const not dropped. Wait, reference and top level const dropped. Cool. Reference is dropped over here. Cool, but we see that it's const, so we keep it. Const dropped, const reapplied. Cool. Hmm. Auto end. Oh, right. Since and wasn't dropped, so okay. Reference dropped and reapplied. Low level const not dropped. And in this case, const reference dropped and reapplied. Low level const and not dropped. We covered the case for reference 1 in the prior example. For reference 2, this is similar to reference 1 case, except we are reapplying the const qualifier, so the reduced type is const string. Things get more interesting with reference 3. Yes, normally the reference would be dropping first, but since we are reapplying the reference, it is not dropped. Yeah, it is not dropped. This means the type is still const string and since this is const in a low level const, it is not dropped. Thus the reduced type is const string and the reference force case works similarly to reference 3, except we have reapplied the const qualifier as well. Since the type is already reduced as a reference to const, us applying reapplying const here is redundant. Yeah. That said, using const here makes it explicitly clear that our result will be const, whereas in the reference 3, the constness of the result is implicit and not obvious. If you want a const reference, reapply the const qualifier, even when it's not strictly necessary, as it makes your intent clear and helps prevent mistakes. What about const expr references? Const expr is not part of an expression type, so it is not reduced to auto. It's not part of the expression type. Okay. A reminder: when defining a const reference, example const int and the const applies to the object being referenced, not the reference itself. Yes. Uh, const int and const applies to the object being referenced, not the reference itself. And this is not allowed, right? This is clearly not allowed. Okay, back again. So a reminder: when defining a const reference, example const int and the const applies to the object being referenced. Okay, that determines. Now the reference itself, when defining a const expr reference to a const variable, example const expr. Okay, when defining a const expr reference to a const variable, example const expr const int and we need to apply both const expr, which applies to const with the reference, and const, which applies to the type being referenced. This is covered in 12.4 and value reference to const. Okay, so okay, string view hello hello implicitly const. Yeah, it's implicitly const, right? Then we have int main over here. So okay, Get const reference. It returns a const string view. It's const expr also. Function is const expr returns a function is const expr returns a const this. Okay, so it's string view and function returns to string view and return hello. Cool. Int main there's const expr auto ref to get const reference. Okay, I think something is going over my head. I think I need to reread some stuff. I understand all of this. I think I have missed some parts over here. I think I will understand uh, like eventually, but okay. Uh, yeah, it's going short. Const int and the const applies to the object being referenced, meaning you can't modify the object, but the reference itself can be reassigned if it's a non-const reference. Const expr, const int and both const expr and const are important here. Const expr makes the reference itself constant. That is, the reference cannot be changed, while const applies to the object being referenced, meaning the object cannot be modified. The reference itself cannot be reassigned after initialization. The const applies to the object being referenced, meaning the object cannot be modified, but the reference itself cannot be can be changed to refer to another object because the reference is a constant one set. So when you use const int, both the object being referenced is read only and the reference itself is read only as well. It can be made to refer to different object once it's initialized. Yeah. So what does const expr make constant? So what does const expr make constant? What is its use over here? In C++, const expr is a keyword that ensures compile time evaluation. When used, it guarantees the value is constant and can be evaluated at compile time rather than at runtime. In the context of reference, the behavior of const expr is different from const. Use of const expr with references. When you write const expr const int and, you're doing two things. Const expr. It makes the reference itself constant in the sense that the reference cannot be changed to refer to different objects after initialization. Hmm. This is similar to const, but const expr has the additional property that it enforces compile time evaluation. In other words, the reference must point to a value that can be modified, that can be evaluated at compile time. This still means the object being referenced is constant, so you can't modify the object it points to. I still don't get the use of const expr. What is the use? When we are initializing references, it is done directly. So it okay. I don't get it. I simply don't get it. Fine, whatever. Get const reference. There's return hello. Sorry. It returns a const expr with string view hello. Auto const expr is dropped. Const is also dropped. Reference drop and oh yeah, it's a string view reference. So the reference is dropped, const is dropped, const expire auto this, const to string view, reference dropped, and top level const drop, const expire applied, implicitly const. Yes. This auto and ref3. Reference reference reapplied and it remains const. Reference reapplied, low level const not dropped. Yeah. Reference reapplied, it remains const. Yeah, const expire applied. Cool. Type direction and pointers. Unlike references, type direction does not drop pointers. Okay, yeah. So string. Yeah, cool, cool. We can also use asterisk in conjunction with pointer type direction, auto pointer to make it clear that the direction use type is a pointer. It's a function that returns a pointer. This is cool and this is cool too. The reason that references are dropped during type direction but pointers are not dropped is because references and pointers have different semantics. When we evaluate a reference, we are really evaluating the object being referenced. Therefore, when reducing a type, it makes sense that we should reduce the type of the thing being referenced, not the reference itself. Also, since we deduce a non-reference, it is really easy to make it a reference by using auto AND. If the type direction were to deduce a reference instead. Syntax for removing a reference. The syntax for removing a reference if you didn't want it. If type direction were to reduce a reference instead. On the other hand, pointers hold the address of an object. When we evaluate a pointer, we are evaluating the pointer, not the object being pointed to. If we want that, we can dereference the pointer. Therefore, it makes sense that we should deduce the type of the pointer, not the thing being pointed to. Cool. The difference between auto and onto pointer. When we use auto with the pointer type initializer, we the type deduced for auto includes the pointer. So for pointer one, the type substituted for auto is string pointer. When we use auto pointer with a pointer type initializer, the type deduced for the auto does not include the pointer. The pointer is reapplied afterwards after the type is reduced. So for pointer two above, the type substituted for auto is string, and then pointer is reapplied. In most cases, the practical effect is the same. Pointer one and pointer two both reduce to this. However, there are a couple of differences between auto and auto pointer in practice. First, auto pointer must resolve to a pointer initializer, otherwise a compiler error will result. Wait, what are you saying? So okay, it returns this. When we do this, so string because we dereference the get pointer. Yeah, get pointer comes over here. We dereference that, and this is auto. So auto is string. Yeah, correct. When we do this, we dereference that. This is string, and this is forced to be a pointer. Does not compile. Initializer does not. Initializer not a pointer. Cool. This makes sense in the pointer for case. Auto reduces to string. Then the pointer is reapplied. Thus, pointer 4 has type string, and we initialize a string with an initializer that is not a pointer. Second, there are differences in how auto and auto pointer behave when we introduce const into the equation. We'll cover this below. Oh, I'm going to take a break after this. Okay, 49 minutes. Cool. Time direction and const pointers. Since pointers aren't dropped, we don't have to worry about. But with pointers, we have both the const pointer and pointer to const cases. Let's start. Okay, this. const dot get pointer. Yeah, get pointer gets string, string const. Yeah, cool. This is a low level pointer. Okay, okay. Wait. So get pointer, what this does is we get string pointer. We get pointer over here. Auto becomes string pointer, and const is applied. So boom, it's a low level const. Get pointer over here. Auto const. This is low level by default. Const auto pointer. So auto is forced to be string, and then we apply const. Yeah, okay, so it's string pointer, and then it's const. I did not understand that. When we use either auto const or const auto, we are saying make the reduced pointer a const pointer. So in the case of pointer 1 and pointer 2, the reduced type is string pointer, and then const is applied, making the final type string pointer const. This is similar of how const int and int const mean the same thing. Yes. However, when we use auto pointer, the order of the const qualifier matters. Okay, a const on the left means make the reduced type a pointer to const. A pointer to const. Okay. Whereas a const on the right means make the reduced pointer type a const pointer. Thus, pointer 3 ends up as a pointer to const, which is this, and pointer 4 ends up as const pointer, which is this. So the pointer cannot be modified. Cool, cool. I got it, I guess. Let's look at an example where the initializer is const pointer to const. Hmm. So string and okay, I'm going to do this. I'm going to when. Let's go. So s okay, const string pointer, const pointer. So the pointer cannot be modified as well as the reference, not reference. What is it? The object cannot be modified. Yeah, address of s. Cool. Auto pointer one pointer, which is this. Well, the top level const is removed. So I guess this. So pointer cannot be modified. So pointer can now be modified. Yeah, pointer one can be modified. Cool. So boom, uh, top level is removed. I guess this remains auto pointer. Const is removed. Boom. This becomes std string. Wait, std string. Yeah, okay. Auto const. So this is the same thing. So const is reapplied. So it's the big one here. Const with string pointer const. The order doesn't matter. It's the same thing. Cool. Auto pointer, now the order matters. So auto pointer, we are saying that this is a string pointer and this should be const. So this will be this will be like a string pointer const. I need to understand stuff, bro. Okay. The pointer one and pointer two cases are straightforward. The top level const, the const of the pointer itself is dropped. Cool. So the const on the pointer, the const on the pointer itself, like ptr is equal to x, that is not possible now. The level of const on the object being pointed to is not dropped. So in both cases, the final type is const should string and const should string pointer, right? The pointer 3 and 4 cases are also straightforward, which is these one. Yeah, as we said, it doesn't matter. The top level const is dropped. Boom. But we are reapplying it. The low level const on the object being pointed to is not dropped. So in both cases, the final type is this. Okay. So here point. So when we do this, reference cannot be modified. When you do this, the top level is removed, and this is just applied to the const. Okay. The pointer 5 and pointer 6 cases are analogous to the cases we showed in the prior example. In both cases, the top level const is dropped. Okay. So top level const is dropped, which is this one. For pointer 5, the auto pointer const reapplies the top level const. So the final type is this. Yes. For pointer 6, the const auto pointer applies const to the type being pointed to, which is in this case was already const. So the final type is const to string pointer. Yes, okay. In the pointer 7 case, we are reapplying the const qualifier twice, which is disallowed, and we cause a compile error. And finally, in the pointer 8 case, we are applying const on both sides, each, which is allowed since auto pointer must be a pointer type, so the resulting type is const this. Because we are trying to const to string pointer, low level const. The string can't be modified. Pointer const pointer, top level const. The pointer itself can't change. So pointer is a const pointer to the const to string. Now this line, const auto pointer this. What happens with auto? Auto reduces the type of pointer, including its top level constant. So auto already becomes const to string pointer. Man, you're tripping. I'll look after this afterwards. Okay. If you want a const pointer, pointer to const, or const pointer to const, reapplying the const qualifier even when it's not strictly necessary, as it makes your intent clear and will prevent mistakes. Cool. Consider using auto pointer when introducing a pointer type. Using auto pointer in this case makes it clear that we are introducing a pointer type. Enlists the compiler's help to ensure that we don't use a non-pointer type and gives. Sorry to hear about. Sorry to hear about your headache. Let's recap the most important points quickly. Yeah, okay. Let's do it. Top level versus low level const. A top level const applies to the object itself. Example this, or example this. Yes. A low level const applies to the object accessed through a reference or pointer, which is this. So the object cannot be modified. What type direction reduces? Type direction first drops any references unless the reduce type is defined as a reference. For a const reference, dropping the reference will cause the low level const to become a top level const. I don't think I want to read that. I will read this chapter again. That's fine. Off camera. But this is a headache. Oh boy, this is a headache too. Okay, off camera. I'm not reading this right now. I'm tired. Yeah, thanks for watching this video. I'm Aditya Pachorni, and I am an engineer for fun. Bye.